So Aijmn, this fourth order tensor, in the most general form has 81 components. But we don't need that much generality, because for an isotropic fluid, and that's what we're interested in, the stress-strain relationship is independent of the orientation of the coordinate system. And so, as a result, A here, this tensor A, has to be also isotropic. And for a isotropic fourth order tensor like this, it can be shown that really you're only left with three unique scalar elements. And the expression then becomes, in general, Aijkl is mu the point being that our isotropic fourth order tensor can be expressed in terms of the isotropic second order tensors delta ij. And this goes back to Aris 1962. And the three coefficients here, mu, mu dash, and lambda, are three scalar coefficients that are thermodynamic properties of the fluid. In particular, as we will see, they represent the viscosity. And since Aijkl, in our case, this thing actually has to be symmetric in Ij and Kl, we then realize that mu and mu dash have to be the same. And you are left with just Aijkl is 2 mu and so we're only left with two coefficients, 2 out of 81, which is quite remarkable. So we can plug this now into our equation 1 up here, and the stress tau ij is related to the strain rates via these two coefficients mu and lambda. And just to clarify, symmetric in Ij and Kl up here because tau ij is symmetric, and so is skl, or smn, as we have written it up on number 1. We can do the contractions between the Kronecker deltas, like delta ik here, and the strain rate tensor, skl. And we can do that for both terms. So then I'm just left with tau ij is 2 mu sij plus lambda skk delta ij. But we know that tau ii, because it's the deviatoric stress tensor, so it's shear, pure shear, we know that this is 0. And so that would mean that 2 mu sii plus lambda sii delta ii is 2 mu plus 3 lambda sii. And maybe I should call this here kk so that we don't get confused with our repeated indices. But what's SKK or SII? Well, remember that Sij is a half dui dxj plus duj dxi. So Sii is nothing but the divergence of u. And we've shown that before. So that means that 0 is 2 mu plus 3 lambda times the divergence of mu. Of course, we can cancel that, and we find that lambda is minus 2/3 of mu. And we're left with only one constant of a relation between tau and s. So let's write our constitutive equation as tau ij is 2 mu Sij minus 1/3 divergence of u times delta ij. And for an incompressible fluid, where the divergence is 0, we're just left with tau ij is 2 mu Sij. And this should be familiar to us from one of the first lectures that we had, because it is just Newton's law of momentum flux, relating the stress tensor with the viscosity mu to the strain rate. Plug this into our expression for Tij. Yeah, so we had the stress tensor as a sum of the isotropic P component and the non-isotropic deviatoric stress tensor. And so now we have Tij is just minus P delta ij, nothing changes here. But then we have plus 2 mu, and this really is P bar, plus 2 mu Sij minus 1/3 skk delta ij. And this eliminates all unknown components of Tij and introduces one unknown component, P. Remember that mu here is just the viscosity, so that's just a material parameter and not one of the unknowns of the equation.